Okay, so welcome everyone to Guided Study Group Week 7 of Statistic 100. Today we're going to be working on Lesson 7 and kind of like review it before going to some of the practice problems. I apologize to any of the noise gonna occur in this video because I forgot my headphones, and so it's kind of like I try to find quiet corners in the public, but this is like the best I can find right now, and I apologize for the noise. So today we have lesson 7. Is the relationship between categorical variables. It's just kind of like another aspect of how to find a relationship between variables. Last week we're talking about measurement variables or quantitative variables. This week we're going to be working on the relationship between categorical variables. And there are not that many things to pay attention to. So we have things that we need to focus on, say, first is the contingency table. So this is how the data, the categorical data is going to be represented. And it's usually written in the form of m multiply n. So you have m rows and n columns. We also have conditional percent, which is like, say they're asking about a percentage of something and condition on something else. So it's going to be condition on the possibilities or the groups. And we're going to see that better in the review problems. Or you can actually work on the test yourself part in the online notes. I think it's really helpful to understand exactly what is conditional percent and how they're gonna phrase it in the questions that are gonna be asked. Then we have cluster bar graph. So it's like a way to cluster bar graph is like you have each of them like this, and they just represent like in the form that can help people see like the different ranking in each different variables that we're talking about. Say this is group 1, group 2, group 3, and then we have color coded for each of these. Say like that. Each of them is going to represent a different thing, and by representing in a bar graph, we can usually see the order of each of the categories, say like what is rightly dashed, and then like this. And like each of them is going to be represented, and then we can draw conclusions on that. We also have things like the 2x2 table. It gives information about what is the undesired outcome. So say if they're asking you what is the odds or what is the risk of something, so that something is going to be the undesired outcome, and that's what we are looking for the odds. And then we have the definition of odds and risk. So odds is different from risk, even though in reality people tend to like confuse between these two or use them use these concepts interchangeably, but they're not the same. So the odds is defined as the number of proportion with a trait number, with a trait, and the proportion without the trait. So kind of like if they're asking you the odds of something happens, so you're gonna multiply the possibility of A and the possibility of A not happening. So it's A bar. That is going to be the odds. And then we also have like BA divided by BA. The odds ratio. So the odds ratio is like, we have to understand what's the interpretation. So the odds ratio is defined as odds of some outcome 1 divided by odds of some outcome 2. And so each of the odds is defined this way. So it's kind of like equal to PA multiply P bar divided by PB. With A and B be the two outcomes that we're talking about. The odds ratio is the same regardless of where you condition it is. Is it conditioned on the explanatory variable or the response variable? So it doesn't really matter if it's odds 1 divided by odds 2. If it's like odds of, if you say this one is A and B is based on the possibility. So if you take the odds ratio based on the group, say group 1 divided by group 2, it's going to be the same. And we're going to see that in one of our review problems. Then we have the risk. Risk is kind of like, it's basically just the probability of an adverse outcome. So just say you have 10 different outcomes that can happen, but 6 of them is not desirable. So then the risk is that you have 0.6 of the outcome is not desirable. Now give me a second. The air conditioner is really, really hot. Okay, so that is the risk. Then we have relative risk. Again, it's going to be risk of some adverse outcome 1 divided by risk of adverse outcome 2. And this is not similar to odds ratio because whichever risk depending on is going to be different in the order. And the relative risk is usually used to compare risk between groups and between different situations. So say if you have like what is the risk of like women, how likely is women compared to men to maybe get a disease or something, then that one is we're talking about increased risk. We're talking about relative risk. However, when we say something like young adults is less likely, it's like 30% less likely than all the than elder people in obtaining maybe asthma or something, then that percentage is called the increased risk or decreased risk. So just like the difference in percentage of risk. And this is found by relative risk minus 1 multiply 100%. Yeah, that's also used to compare risk between groups and between different situations. But you gotta notice the difference in how we phrase these risk and increased risk thing. Therefore, we also have the last part is some misleading perceptions. So kind of like these are some of the things that people usually like mistaken. First thing is baseline. So in a lot of times, like when people hear about, okay, this thing is maybe like 50% more likely to cause you maybe cancer, then people usually tends to like not use that product anymore and just consume the other product, even though in reality the risk might be really small. So say one have the risk of 0.002 and the other one have 0.003. If we look at these numbers, it doesn't really make that much of a difference. However, if we find the increased risk, then it's going to be 0.003 minus 0.002. Oh no, divided by 0.002 minus 1 multiply 100, which is going to give us 50%. Now that 50% sounds very significant, but in reality, if you look at these percentage, it doesn't really make that much of a difference at all. Therefore, we have to look at what is the baseline, like what is the actual percentage that it used to compute to get this 50%, to see if there's the difference should be like, you know, is noticeable or not. Then we have another concern is whether the risk really pertains to you. To say risk calculations are very conditional on specific population or situation, and it's really important to consider how that risk really relates to you. To say we're talking about, I think in the online notes there's a very helpful example where they talk about sports and athletes. So what happened is like they say some sports are more vulnerable to cause it's more likely to cause knee injuries than the other sport. And so if we don't, and like it's like the risk is like two per like 10,000 games. So in that case, if you only play like 40 or 50 games in your high school, and it's not even like that intense, to say professional football is very different from, you know, amateur football or like the type of football that we actually play in high school. So it's really, really different, and the risk that they calculated might not really pertain to you because it might just be applicable to athletes or professional players instead of you just like a high school regular players, and the intensity, as I say, or like the chance of being in contact or get hurt during the sport is really low. So yeah, it's really important to consider the baseline and whether the risk that they calculated, the situation, and the population is related to you or not. Finally, we have the important concept of Simpson's paradox. So it's saying a Simpson paradox is that an observed association between two variables can change or even reverse direction when there's another variable that interacts strongly with both variables. So say, I will say again using the example in the online notes, is that sometimes when you have, say, you calculate a percentage of someone in Democrat and they vote, and in Republicans they vote, and in different area, if we, even though sometimes we can have a percentage of maybe Democrats that actually vote higher than Republicans in both regions, the total populations, like the percentage of Democrats that actually vote in the populations might be lower than Republicans because of the numbers, and that happens a lot in reality because percentage only show you like what proportion, but it doesn't actually show us the actual effects of like how big the population actually cause that proportion. So if you say 3/5 is the same thing with 30/50, right? But this is a difference in the population example that we're talking about. So that's the Simpson's paradox. There's not really that much new materials in these sections, but a lot of the concept is now on a higher level. So it can be confusing for people who doesn't actually get categorical variables at the beginning and kind of like struggle at a few first lessons. So right now, if you need to catch up, please feel free to review the own categorical variables and some of the problems that we already talked about in before your midterm exams. Here we're just gonna work on continue on discussing statistic 100 and categorical variables on a higher level. Now we're gonna have some practice questions and problems. So the first question say, yeah, again, stop me if you want to work on it on your own. It's thought that there may be a link between gender and heart disease. Sorry, I just typed this one this morning. Heart disease. Suppose we collect the following data. The increased risk for male to females in this problem is 30. Which of the following is the correct interpretation of this increased risk? And this is the data that we have. So let's see, males are 30 times more. First of all, increased risk is represented in percentage. So when they say the increased risk is in this problem is 30, which means that the 30% male has 30% higher chance to get heart disease than females. So if we look at the answer, 30 times is not right. So A and B is not right in the times because increased risk is calculated and represented in the form of percentage. So A and B are not right. Males have 30% with smaller chance of having heart disease. No, it's not right. Actually, it's higher chance of having heart disease. So D is the correct answer. And we have question 2. A study done by the Ohio State University Medical Center examined whether or not taking an aspirin a day would help colon cancer patients reduce the chance of getting subsequent colon polyps. 635 patients with colon cancer participated. 317 of them were randomly assigned to the aspirin group, and the other 318 patients were assigned to a placebo non-aspirin groups. 54 patients in the aspirin groups developed subsequent polyps, compared to 86 patients in the non-aspirin groups. Many confounding variables were controlled for this well-designed randomized experiment. What percentage of all the patients in this study did not develop subsequent polyps? Now, first of all, question 2 is asking percentage of all patients in this group did not develop subsequent polyps. So we have to find what the total of the patient is 635, and that did not develop subsequent polyps. So we just look at the did not develop polyps, and they don't care about if that person took aspirin or did not take aspirin. So it's going to be 495. So the percentage here is going to be 495 divided by 635. So that's my final answer. So the key in these kind of questions, before I proceed to other examples, is that you have to understand what the question is asking and avoid looking at the answer choices. Trying to derive your answer on your own based on the given data before you're looking at the answer. So it's gonna like reduce your bias and also not gonna kind of like reduce the chance that you're gonna choose an answer just by thinking it is what it is, but it is not. So like try to avoid like some, I would say, silly mistake to be made just because you know how to do this. So just take like a few seconds, like 1 minute to work on it alone before choosing the answer. Now it's the same thing, question 3, but it's asking what percentage of patients on the placebo did not develop subsequent polyps. So they want you to choose whoever did not take aspirin and did not develop subsequent polyps. So it's going to be 232 on the place. Now let's see what is it divided by. Now it's on the placebo did not develop subsequent polyps. So it's going to be 232 divided by 495. So they're asking, okay, it's asking on among the people who use the placebo, like what is the percentage that did not develop subsequent polyps. So it's going to divide by everyone doing the placebo. Well, actually, no. Everyone using everyone using the placebo, which is 318 people, and who did not develop polyps, which is 232 people. So this is the answer for us. Again, if you have any questions, please feel free to email me or like mute myself during the thing and that, like maybe get a minute or two to think on it on your own before proceed. Kind of like just catch up and yeah. Now we'll do question 4 again. If you want to work on it on your own, please feel free to stop me. Use the table below showing the record for the Pittsburgh Pirates in the 2014 season to answer the following questions. Okay, so first one, what percent of their home games did the Pirates win? So basically, you're gonna say what percent of their home games. So of their home games is the total that you're gonna divide it by. So home games is 81, and they win 51. So that is 51 over 81. Now the next one, what percent of the Pirates win were at home in 2014? So the total wins. Percentage of wins. So the winning is 51 plus 37 is 88. We're at home. So at home and win is 51. So that is the answer for the second one. What was the odds that a Pirates victory came at home? The odds that Pirate victory came at home. So odds is when you have, so the outcome you're looking for is victory at home, right? Victory is 51. So you only look at whatever is the winning. So at home is 51. And what is the winning that a victory is not at home, which is going to be away, which is 51 over 37. Now, it's asking the last one. The third question is kind of like a little bit challenging because people might think, okay, the undesigned, the odds of that proportion of that outcome and proportion with down. Let's see what is the odds again. Give me a second. We can come back to the definition. So the odds is saying number of proportion with a trait and number of proportion without a trait. So a trait here that we're looking for is the odds of the trait here is victory came at home. So came at home is the trait, and without the trait it's gonna be not at home. So it's gonna be a winning and not at home, which is with wrong away games, which is 37. Now the last one is gonna ask us true or false. The ratio of the odds of the Pirates winning at home to the odds of them winning on the road is the same as the ratio of them being at home for a win to them being at the home for a loss. Now it is really confusing to read this sentence. So what I decided to do, not just using the property of the odds ratio, but also there's another way to do it, is that you guys actually write down each of the whatever they say is equal. So the first one is the ratio of the odds. So the odds ratio of the Pirates winning at home. So odds of Pirates winning at home is 51 over 37. Odds of them winning on the road is going to be winning at home. Oh, so the ratio of the odds of the Pirates winning at home is going to be 51 over 30 actually, because it's asking of winning. So winning here is the different thing. So at home, so the odds of the Pirates at home, and so the trade here is going to be winning, and without a trade, it's going to be losing. So it's 51 over 30. Now the odds of them winning on the road is going to be 37 divided by 44. So this odds ratio is going to be 51 over 30 divided by 37 over 44. So this is the first odd. Then we have a second one. The ratio of them being at home for a win. Being at home for a win. So at home here is going to be, the win here is going to be, hang on. At home here is going to be the trade. So it's going to be 51 over 37. So we're going to just look at winning. And at home is going to be the trade, and 37 is going to be without a trade, which is not at home. Being at home for a loss. So it's at home. So when we have losing and the loss is 30 at home, and then away is 44. Therefore, the second odds ratio is going to be 51 over 37 multiplied 44 divided by 30, which is the exact same thing as here. So this is the second way, and also kind of like the harder way to do it. But if you were able to write it down, then it means that you can understand what exactly is going on. Otherwise, you can just use the property of odds ratio that we talked about before. Again, if you have any questions with this last part, please feel free to email me, and then I'll try my best to explain to you guys. Now, let's go to, I think it's the last question of today. Suppose the percentage of men who graduate within 4 years of studying college is higher for engineering majors than for education majors, and the percentage of women who graduate within 4 years. So, first of all, men who graduate within 4 years studying college is higher for engineering. So, men, you have P engineer is higher than P education for graduate in 4 years. And then it's the same thing. The percentage of women who graduate within 4 years of studying college is also higher for engineering majors. So it's the same thing for women. So you have engineering is higher than education. Therefore, what is the correct statement below? Stop me if you want to work on it on your own. I'm sorry, forgot that part. A, this means most engineering majors graduate within 4 years. Well, you don't know actually, because it doesn't say anything about what percentage in College of Engineering. So it can be 30% of just the population, but it's still higher than education. But it doesn't, then 30% of engineering is definitely not the most engineering majors. It's just like a portion of it, but it's still higher than the percentage of education. So A is not right. B, it's still possible for the percentage of all engineering majors who graduate within 4 years to be lower than the percentage for education majors. Now this is the correct one, and this actually is the Simpson paradox. So say if you can just, if you just like plug in some numbers that satisfy that, I'm sure you can find definitely more than one combination that can show you this problem. And if you Google it, I would say I think there were like a bunch of these kind of questions online. Not just because like it's just like some problems so that you can know, and then you know what kind of questions they're gonna ask you in the exam, but in reality, this is actually what happened. If you look into the data of companies or even like the place that you're looking for, you're gonna see some of these paradoxes. So it's B. Let's see the other, what's wrong with the other answers. This means the percentage of all engineering majors who graduate within 4 years must be lower than the percentage for education majors. Well, I mean, technically talking about, it's actually, it should be the other way around. But then you don't know if it's certain or not. And here, the way that I concluded is that it's a certain thing that happened. And so C is also not right. That means the percentage of all engineering majors who graduate within 4 years must be higher than, again, same thing with D. There's nothing that is certain about this. There's something that can possibly happen that can completely change the answers. Now, having said that, yeah, that's everything I have for today. Again, if you have any questions during the week, please feel free to email me and let me know, and then I'll try to answer them. The next section is next Thursday, July 5th, 10 p.m. Eastern Time. Hopefully everyone already enjoyed their 4th of July holiday on that day, so before that. So you're gonna be ready for Statistics 100. Now, all right, I'll see you guys next week, and have a great weekend.